Okay, I think we can officially start. This is preconditions, postconditions, invariants, and how they help write robust programs. Welcome, everyone. Thank you for choosing this talk. My name is Andrzej Krzemieński. I work for Sabre Polska. I'm also a member of Study Group 21 in ISO C++ Standards Committee, which deals with contract support. And this is contracts that we are going to talk about, function contracts. And function contracts are actually the key component here. If we keep track of our function contracts, then we enable us the control over the correctness of our program. So the plan for today's talk is to go over function contracts, what they are, then to show you the strong and weak contracts and how the choice between them affects our ability to control the correctness of our programs. Then we'll look at the contract violation as a tool offered by strong contracts for identifying bugs. Then we'll see how we enforce our contracts, even in today's language, like using constraint types. We'll see how adding further features to the language can make the contract enforcement even better. And if time permits, we'll have a look at the difference between a bug and the symptom of a bug, how it's easier to treat symptoms, but why this doesn't actually fix bugs. And the first concept that we will be going back to in this talk is this order dependency of things we have to do when writing new code. This is, we start with the need to do something with the code in our program. Then we design an interface that will address this need. And then when we have the interface, we actually provide code that will implement this interface. And it's not a very rigid structure. Often it happens that when we provide the implementation, we realize that the interface will not do and we have to change it. Similarly, when changing the interface, we may find that we actually need to redefine the need, and this is all fine. The key here is that at each point, when we have an interface, we have to keep track of what need it actually addresses, because otherwise there is no way to actually tell if our interface is correct or if it's good. And similarly with the code, we have to know what interface at the given moment we are implementing and indirectly what need. So let's start with the first need here. Imagine that we have a program that already deals with aircrafts. We'll be we already store a collection of aircrafts represented as pointers. So apparently the memory is managed somewhere else. And we will have to sort those aircrafts by weight. And we can immediately see that there is a certain abstraction gap here because I'm talking about the aircrafts. And what I've actually written is memory addresses, because pointers are addresses. While the first one is an abstract notion representing something from the real life, the other is just numeric values. But this is not that bad as it could have been if we used a dynamically typed language, because then we would get an equivalent of void star, which is even a bigger gap. And here we have this type aircraft, which is already huge support from the type system. Because we can expect that it will have member weight, which will give us exactly the information we need. It is a guarantee that if the author of this class aircraft forgot to implement this weight, we would get a compiler error. But this help from the type system is not full. Because for instance, I don't know if this weight is actually in kilograms or pounds. And there is another abstraction gap here because I'm talking about weight, but I've really typed type double. And NASA learned it the hard way, the difference between the two when they lost their Mars climate orbiter because of the unit mismatch. One part of the program thought it was newtons per second, the thrust. The other thought it was pound forces per second, then the orbiter couldn't land. So we will have function is lighter as a predicate for sorting. That will take 2 pointers to aircrafts. And again, the abstraction gap, we mean aircrafts, we actually type pointer to const class aircraft. And we will defer to another function, not a function, to a language feature, which comes with its own contract. I mean pointer to reference. It is a feature that turns addresses into memory locations or into accesses to memory. And we have to make assumptions to make it work. And if we consider that memory is just a sequence of numbers, there's a lot of assumptions that we have to make this work correctly. So there is an expectation of our pointers that it is not null, and this is maybe the most obvious one. But the other is that under this address, we actually have to find a living object of type aircraft or compatible. And while the first one could be checked at runtime, the other one, there is no way to check it. Our callers will have to somehow make sure that the objects really are there under this memory. So this is our first example. In this talk, we will be tormenting 2 examples most of the time. So let me give you a second one before we go further. There is another need in perhaps a different program. We will be getting integer values, and we need to check if they fall within a certain range. We can get the limits of this range from the configuration. There will be an upper bound and lower bound, and we have to check if the ints fall inside. So the interface may be something like this. We have function is in range, it takes the value, takes the lower bound, upper bound, and we check if the value is in range. And again, there is abstraction gap here, because I'm talking about a close range, and you actually see 2 objects of type int, low and high. Now, compare this to another function, f, that takes 3 integers. From the type system perspective, they are indistinguishable. They have exactly the same type. But there is a huge difference between the 2. The first function is in range. We know exactly what it does and how to call it. We know what to expect of it, how it will interpret the inputs we give it, when we can call it. And about this function f, we know nothing. Can we call it now? Do we have to call something else before we call this? What it will get? We don't know. We will probably don't know if it's safe to call it. The difference between the 2 is in function contract. It is all this information that we have, even including in comments, that helps us or that gives us the information that we need to call the function correctly. And because of this abstraction gap, it is possible to call our function with values that fit into the type system, but they don't fit into our abstraction. So this is a short overview and introduction to function contract. It is all you need to know to be able to call the function correctly. It includes things like how the inputs are interpreted, how you should interpret the output, what are the limitations of the inputs, what other functions you have to call prior to calling our function, what other effects it has, and probably more. And while some parts of function contract can be expressed directly in the language, like the number and the type of the arguments, or whether they are consts, other parts cannot. Like we cannot express in the language the exception safety guarantees or the disallowed values. And how is it different than the definition of the interface? Well, if we adopt the wider interpretation of the interface, they are the same. But conventionally, I think when we use the word interface, we mean the subset of function contract that is expressible in the language. But the interface cannot exist without the function contract. Okay, if we consider the 2 functions from the C library and therefore from C++ library as well, We have setLocale and strlen, and they both take const star. But one, in case of setLocale, you can put a null pointer as locale, and this is fine. This has a special meaning, which says we are not actually setting the locale, we are just getting the current locale and nothing more. But in case of strlen, if you pass a null pointer, it's just a bug and will likely crash your application. The point here is that from just inspecting the type alone, you cannot know how to call it, to call those functions safely. You have to read the documentation, for instance, to be able to do it. And before we go to the next section, let me check if there is any questions asked. No, okay. So strong and weak contracts. Given the fact that there are the combination of values that will not work for our abstraction, and the other observation that the combination of wrong values can be expressed as a C++ expression, we can try to answer the question what we want to do if for some reason someone passes us the argument to our function so that in case of this range, low is greater than high. And one answer that people sometimes give is we have to change our contract. And now say you can see that the contract is changed because the comments are bigger. That if low is less than equal high, then we check if value is in range. If not, we will return, say, false. And I will not be telling you why people do it because I fundamentally disagree with it. I will just tell you why you should not do it. And the list is like this. We have weakened the abstraction this way. We have increased the complexity of our program for no good use. We give only a false sense of safety here, and we have missed the opportunity to detect bugs. And let's go through them one by one. What do I mean by weaker abstraction? We are no longer talking in terms of ranges. Now we are talking about integers. I'm giving you even in the comment the comparison between two ints. You have to compute it. Then it will do something based on those integers. We are talking about the comparisons of integers. We have lowered the abstraction. The point of the program of introducing the abstractions is to allow us to even manage big programs, because otherwise there are just accesses to memory and nothing more. And our brains cannot actually work with this amount of instructions. So we have to build abstractions to somehow manage the thinking about the program. And now I'm forcing you to go lower level and to drop the abstraction, only to handle this case of invalid values. The complexity is increased now because the if in the comment will be reflected by an if statement in the code, most probably. So there is more code paths, more places where I can plant bugs, more unit tests that I have to write. The program will be bigger and for no good use. Consider the other function is lighter for 2 aircrafts. I could say that if A or B is null, I return false. But what will you do with it? I mean, why would you ever pass null pointer here consciously? And now I have to deal with it. I have the second responsibility to manage. So I actually broke the single responsibility principle because my function now not only checks weights of aircraft, but also looks for null pointers. And you do not really get the safety from this because I'm protecting against one value null. But what about the other values? If someone passes me FFFFF, it's also bad, but we cannot protect against it. What about any other values? It is still the user that has to take care of the caller of our function, that has to make sure everything is correct. So if we just protect against one value, we give a false sense of safety. And most importantly, we miss the opportunity to detect bugs. Because what is the reason we will get the invalid input, like low greater than high? This is probably because, for instance, someone switches the order of arguments. Someone may think that the val goes at the end because this is what other libraries do, whereas we expect it at the beginning. This is something that we would like the tools, our program to detect, but we will not be able to detect it if we say every combination of values is good and handled by us. We have to have a way to say that some values are bad, because this will be our criterion for detecting bugs. So to put the same things in positive terms, the strong contracts are recommended because they allow us to provide simpler abstractions that we can manage. They discourage bugs because of that. And if you still plan them, we have means of actually detecting those bugs and taking some actions. So rather than weakening our abstractions, we should look for language features that enforce them. And one of tools that will help us is contract violation. Again, before we go there, let me see if there's any questions. No, I cannot see any questions. Our function is lighter for 2 aircrafts, expects 2 pointers, and it is not unlikely that it will be implemented this way. We just use the indirection to get the 2 weights. So we will differ in our implementation to a language feature that, similarly to our functions, was designed to serve a need. The need is to access an object under a given address. And this feature has a contract. Like there must be a living object under the address A, and a special case of this address cannot be null. And we are lucky that the second part can actually be runtime checked. So a good tool like a compiler equipped with Undefined Behavior sanitizer could inject a check. It could check if those values are, any of those are null, and call abort. And it can do it because the language contract is official. Everyone knows it. It's publicly available. Therefore, any tool in the world, if it wants to, can make use of it. Another use that a tool can make is in a static analyzer. If we make our function inline, which means the body of the function will be available to the static analyzer also at the call site, a clever static analyzer that performs symbolic analysis evaluation of the program can detect that there is a path that leads to null pointer being the reference and can give us the warning. And it can do it because, again, it's official, the contract that null pointer is, you never want to dereference a null pointer. There is a question. Would it be correct to say that contracts are constraints on values like concepts are constraints on types? Yes, I fully agree with this statement. So this is another use that a tool can make. But this is because the contract is official. The same goes for standard library contracts. For instance, std_string has in its contract that the pointer you pass it cannot be null. So if I, by accident, pass the wrong pointer that happens to be null, a clever compiler or UB sanitizer could inject a check like this for a null pointer based on the precondition and call abort. But UB sanitizers don't do it, even if they could. But instead, what they do, and you will often find it, is that whoever implements the standard library will put an assert inside. And this assert can potentially, again, call abort. And the authors of the standard library can do this because the contract for the standard library is official, publicly available to everyone. But this is not the case for our functions. Like, only we know the contract of our functions and maybe our users because we communicated it in HTML documentation. And ideally, we would like for our contracts to do the same. Like if someone puts the arguments in the wrong order, we would like to be able to detect it by any means. And we can approach this ideal, again, by observing that the constraints on values, as one of the participants observed, is something that we can express as C++ predicates. And we'll do it. And we'll call this a contract check. It is something that we derive from function contract. So prior to that, we have to be aware of a function contract. And only when we have this, we can derive a contract check. And contract check can determine that a program has a bug. And the first and most important of those checks is precondition. The precondition is a constraint on values that is supposed to hold whenever we enter a function. And so far, I've been showing you declarations rather than definitions in order to stress that there are two parts involved in it, the caller and the implementer. Because if I show you only the implementations, and we usually see implementations, we start to thinking only in our own terms, in terms of the implementer. And the perspective of the implementer is different. Like here, this may be a possible implementation of function is in range. Those expressions, less than equal, work for any combination of integers whatsoever. So they would work even if you passed low greater than high. And because we see no undefined behavior in the vicinity, we may think that there is nothing for us to do here. But this forgets that the bug that is potentially lurking here is outside our function. This is something we could detect. Another situation is when we have to dereference a null pointer in our implementation. So here is a third function that we have to introduce into the picture. This function checks whether the aircraft represented by a pointer exceeds a certain weight limit. And of course, we will have to dereference a pointer here. But now this threat of potentially invoking undefined behavior starts to cloud our judgment. Now, there is a temptation to avoid this undefined behavior at any cost whatsoever. And this works under false assumption that undefined behavior is somehow more dangerous than having bugs. Or if we put it conversely, that having bugs is somehow more preferred than having undefined behavior. And this also assumes that we can fix undefined behavior or avoid it while leaving the bugs alone. And we usually cannot. So there is a temptation to detect the bad values, at least the subset of them, and nothing wrong with this. But then we have to react somehow. And the reactions are usually bad ones. And it's not obvious that we should actually do it, because otherwise we could just make our function inline. That is, expose its body to static analyzers. And a clever static analyzer could detect that there is a path that leads to null pointer being dereferenced and warn us about it. This would be better than detecting it at runtime, because we can fix it before even compiling the program or before running the program. We lose this possibility the moment we just try to take some action. So one of the possible actions is to just return some safe default. And it works on the false assumption that from within the body of this function, we can know what is a safe default for any possible caller. Like this, we check if aircraft exceeds certain weight, because we don't want it to fall from the sky. So we may say, yeah, if I cannot compute the value, I will just return true to be sure, to be on the safe side. But it's possible, and it somehow assumes that the caller is indifferent to whether we are really exceeding the weight or we don't know how to compute the value. Imagine this use case, that someone uses this function exceeds weight to check if we have enough fuel. That is, we want to actually exceed the aircraft weight, which includes fuel. in order to safely get to some airport. And in this way, the true is actually the unsafe default, and we are doing active harm. So another option is to throw an exception in this case. And it's better because not only do we skip the rest of our function, but we also skip our caller. But it's not ideal either because, again, we prevent any static analysis, static analyzer from detecting a bug because there is no null pointer dereference inside. Also, it somehow assumes that by throwing exception and then catching it somewhere, we skip over the bug and land in a place where there is no bug. But this is not the case, not always the case. Let's consider the other example with is in range. It is different because now this expression low greater than high can be triggered for more inputs because there's many combination of inputs that is invalid here, and we can detect those. And if we throw an exception here, yes, the situation where our immediate caller has a bug and passes the arguments in the wrong order, we will skip over this guy, and maybe it will all be all right. But there may be another reason why we observe the bad values. Consider this example. Now I have put the arguments. This is another caller of our function is in range. The arguments are passed in the correct order. So the first val can be anything because we check it. The lower, this low is 0, and the third value that we pass as high is 100 or greater, because this is how max works. And can this caller ever call our function so that its precondition is violated? It looks like it cannot. But there is a possibility that our program has undefined behavior somewhere else, not in this caller, in absolutely unrelated part of the application. And this undefined behavior the nasty consequence of undefined behavior is that if you hit it, the code that we see, the source code, no longer has any bearing, may not have any bearing or relation to the actual code that is compiled. So what that you see, the 0 and 100 and max, if now the compiler has right to execute any arbitrary code. For instance, it's possible that we have computed lower as 0, then we are computing the upper, and function config get overrides some arbitrary buffers and overrides our lower to have a different value. We cannot see it from inspecting the code. Inspecting the code will no longer help us when we have undefined behavior. And undefined behavior is another reason why we see a contract violation at runtime. And it can happen from things like using dereferencing stray pointers, or bad usage of memory, or even data races. And this is where contracts can also help detect undefined behavior if we are lucky. Okay, so let's continue on the undefined behavior. This is the smallest possible example that can trigger undefined behavior. We create a null pointer, we pass it to a function, and this function dereferences it, because we never do it unintentionally. So there is some contract miscommunication here. What does it mean in the language that we dereference a null pointer? Pointer dereference means we want to go under the address P to get something. But null pointer means there is actually no memory address. So there is an obvious contradiction here. We violate the contract of pointer dereference, and because of that, there is no guaranteed behavior here. And we can call it a bug. We never do it unintentionally. But why does the language not define the behavior in this case? The first answer is because there is no use case for it. We never want to dereference a null pointer consciously. And even if we imagine an alternative language that actually does guarantee you some behavior, the only thing we would gain is to sanction your bug. We would sanction your bugs because the bug is still there, but now we give it some good behavior, whatever good means in this case. I have a comment here. The val that should be between low and high should go between low and high in range low val high. Okay, so I think the comment is that my choice of the order of arguments is in range is not actually intuitive. Yeah, maybe. But this is about what language has to say about the undefined behavior or the null pointer dereference. But if we compile the program, something will happen in the running program. So I see another question coming. Do you think contracts could or would become an overloading criteria? Most certainly not. Because when you select the overloads, it's at the compile time. Whereas whether you get this value or that value is only known until runtime, only known in runtime. So it's too late to overload. And I'm not sure what it would buy us. You could do it for context per functions. But I think this would require a separate dedicated feature. So the short answer is no. Okay, moving on. So if we look at the program as a set of instructions, something will happen when we dereference a null pointer. And there are basically two options. One option is that maybe on your platform, 0 is a valid pointer address, and you will get into the memory under address 0, and you will get some numeric value. You will interpret it as int and compare it against 10, as in our case. And then you will produce some result based on more or less random numbers. And imagine you are running a financial server when bad decisions can cause you huge amounts of money, or they can get you into legal problems even, and you are making your decisions based on random numbers. So most probably what will actually happen is not a random number that you produce, but a program shutdown. It will be shut down not because the compiler implemented some code, but because the operating system will immediately kill your program when it tries to do a bad memory access. And this happens because it's a safety feature that someone implemented in the operating system. This protects the operating system from your program. It protects other programs from your program. It protects you from other programs in order not to do arbitrary damage. So we might try to do the same in our code. Let's go back to our function is in range, check if low is greater than high, and immediately call abort. And it might look like an irresponsible thing because our function used to work for any values. That is under some definition of word work. And now we are trading it for abort. But this is not really the case. Imagine that there is a caller that actually calls our function, and maybe it performs some life-critical computation, but it has a bug, so it wanted to perform a life-critical operation, computation, but it isn't anymore. We have a serious bug with potentially serious consequences, and this is what we are trading for abort. Also, there is we cannot see anything bad with our expression we return today in our today's implementation of this function, but we may change implementation to something else in the future. And if we change it, then the expectation that low is greater than high may become critical. So we are protecting against the changes in the future implementation. We make our interface more stable. And calling abort may seem harsh, but before you protest, consider the positive sides of it. We guarantee that the bugs caused by our callers will not do any further damage beyond crashing the program. So we put an upper limit, even if it's high, on the amount of damage that our application can make. Plus, abort usually triggers a core dump, so if a developer gets their hand on it, they can track the problem down. But can we afford to crash an application, especially if we are in a life-critical system or a safety-related system? And the answer is, hell yes. Let me just give you one example. Imagine a hand tool used by soldiers that tells them, I'm fantasizing, that tells them how many enemies there are in the vicinity. This tool or the software in there had better not crash, because if it crashes, the soldiers are left on their own. But if the only option you have inside the code in one function to either produce random results or to crash, then the situation becomes different. If you return just random numbers, or if you return safe defaults like 0 for integer, and you now start saying that there is, I don't know what to do, I'm telling you there is no enemies in the vicinity, you are doing active harm. Whereas if you just crashed, you are sending a very important message to the users, to the soldiers. You are on your own. Now the application cannot help you. You have to deal with it yourself. Now this is upsetting. This is dangerous. But you are giving the most of the valuable information that you can at a given moment. And then the soldiers will deal with it. Maybe they will be upset. They may be come for to get you for this, but at least you have given them a chance to survive. Because it is never the primary goal of the application to not crash. We write, or we are told to write software to do something, to produce some meaningful results. Our manager never comes to you and say, write me an application, but what do you want it to do? Just not crash. But anything specific? No. It can return any values as long as it doesn't crash. It's never the case. It always has to be some values, and not crash is a secondary expectation. I get a comment here. The soldier may be upset, an understatement if there ever was one. I'm not sure I get it. Okay, I'm moving on. Another thing that we could do, and now you may think I'm crazy, is to deliberately introduce undefined behavior. I make my function isInRange inline. So this is in order to be able to engage my static analyzer. And then I just dereference a null pointer. And this is not just any UB, because analyzers are good at detecting null pointer dereferences, because it's very well understood subject here. And what I gain from it is that if someone passes the arguments in the wrong order, so that the high is greater than low, my static analyzer can see a null pointer dereference and can warn me about it. It couldn't warn me about it before, because then there was no undefined behavior inside. And now there is one. And before you say I'm crazy, consider if undefined behavior is more dangerous than having a bug. Because conceptually, they are the same, but at different level. The bug is a violation of my function contract, and undefined behavior is a violation of the language contract. Plus, I don't expect you to do it unconditionally. In fact, what I would expect to have is a macro like trap, which does two things. Most of the cases, it just calls abort, so I get a guaranteed shutdown of my application. But if we detect that we are in static analysis mode, only then do we turn this into a null pointer dereference. And this way, we get the best of both worlds, of the static analysis and the guaranteed behaviors. And this conditional behavior takes us close to good old macro assert. It is difficult to teach asserts and to appreciate them, because usually when we learn features, we ask, what do they do? And the answer for assert is, it doesn't do anything specific. It can do different things at different times in your program. Because the point of the assert is not to do something in your code. It is to communicate your knowledge to any other parties. Your knowledge about what combination of values or what combination of values is disallowed in this part of the program. Disallowed in the sense that you never want it intentionally. So if the bad values are observed, it is a bug. You communicate formally what a bug is. This is what an assert is for. And you not necessarily have to use macro assert. Like C++ core guidelines recommend using macros expects and ensures. There are two, because one is for preconditions, the other one is for postconditions. But the idea behind them is the same, is that you communicate what is considered a bug when calling your function. And there is also a possibility that even though you have planted those asserts and you're actually evaluating them at runtime, your function is called incorrectly with argument or inverted in the wrong order. But it so happens that the assert evaluates to true. The expression inside the assert evaluates to true. The bad order of arguments, but their values happen to match. And there will be no bug detected here. And this is the property of those checks. They can help, they can prove that you have a bug in your program, but they cannot prove that you don't have bugs in your program. So there are like unit tests or any other kind of tests for that matter. So when we say that we expect A being not null and B being not null, we do not really mean that if they are not null, it is okay. We only mean that if either of them is null, it is bad. And that's all we are saying. So the choice, what the predicate is really saying, yes, I confirm that we have a bug, or no, I cannot confirm that we have a bug. But we can do far better than those integers. What we could do is to wrap the two integers into a class called range and force the users to create this class, the object of this class, whenever they need to compute if something is in range. And if we do this, the moment that the user mixes the order of the arguments and passes them in the other way around, we get a type system error. Now we engage the compiler to check bugs for us and the misusages of our interface. So this is a huge advantage. But if you look at it from the inside, not necessarily inside, but if we look at the contract here, objects of class range will probably expose functions like low and high, the access to their members. And we still expect that this low is less than or equal to high. It's just that we have to express it using different syntax. So did we actually gain anything from this? And the answer is yes, we did, because we now turned a function precondition into a class invariant. So our class will probably look like this. It will have members low and high, and as we can see in the bottom, it will have an invariant. This invariant is actually the only reason why we have this class. If it was not for this invariant, we would just go with stud pair and we'll be fine. But now we have invariants. So it's not only the members that we have, the values, but also a constraint. We guarantee that whenever you are able to observe the objects of this class, low will be less than equal to high. And in order to guarantee that, we cannot expose access to those objects, to these members directly, because the users would do random mess with them. So we will make them private, and we will expose only a constant interface, or constrain the interface if it's mutating, so that we can control how they are mutated. And we can actually express the invariant formally as another member function. There is a comment here, not to mention type safety. It's easy to mix up. Yeah, basically, yeah. It is other way of calling it type safety, but here I think I want to focus on, I want to redefine it in terms of contracts, function contracts, and now we are actually talking about the class contract. So we can actually make the invariant a function that we can actually evaluate. We can put it inside assertion, so whenever there's some public member is invoked, we can confirm that we actually provide this invariant. And we could say in our function, put as a precondition that invariant of range must be met, but we will not do it because it would be redundant. Because this is the nature or even a definition of an invariant. It is something that we expect as a precondition for every function that gets the objects of this type. So it's obvious that, well, int doesn't have a precondition invariant, so there is no precondition of int. Range is a class, it probably has an invariant. The invariant must hold as a precondition. So there's no point in even mentioning it. But it's still possible that when constructing an object of type range, the caller can pass the arguments in the wrong order into the constructor. True, so we have to fix our definition of class range and say in the constructor that L is less than equal to H, because otherwise our invariant will not work. And in fact, we can enforce it. In case of a constructor, it's a bit trickier, but we can do it with macro assert. But the observation here is that invariant is a conditional guarantee. We only guarantee that the precondition, that invariant holds when you respect our preconditions in the constructor or in the mutating functions. So it's an exchange of guarantees here. So some bugs are fixed by using this range because you can no longer provide the arguments in arbitrary order. But some bugs, as we've seen in the constructor, can can just get into our system, especially if we have some function bounds that just returns 2 integers. It's easy to get that wrong, even if we are using ranges. But this is because it is not how you are supposed to use this class. The real good usage of this class if you are able to propagate this type throughout the layers of your program. In our case, if you can teach the function bounds here to speak in terms of ranges, it is only this function bounds that can construct the object with bad arguments. But anyone that reads this value here cannot get it wrong. So what we get from this, if we spread the usage of this abstraction range, is that we narrow the scope of where this bug can enter into our system. And this is technique you should use, but it's not possible to use it everywhere. Like if we consider the precondition to vector element access operator. The I cannot be size or greater, but there is no way you can turn it into a class with an invariant because the range of allowed values changes over time. And classes with invariants can also address the other problem we've seen with kilograms versus pounds. Now we define a class kilograms that has a double inside, but by the virtue of having this class, we communicate also how this value is supposed to be interpreted. Or in other ways, we store the numeric value as a member, and we store the unit as encoded in a type here. Of course, now the constructor will be explicit because we don't know just random conversions from double, or maybe we want to disable constructors altogether and just provide a static factory function that has a good name that tells us what is going on here. And we can fix the interface of our aircraft. And now everything is communicated through the type system. We don't have to rely on comments. So unlike what we are taught in object-oriented classes, the way I think about classes is that you define them either when you have an invariant that you have to reflect, and it maybe sometimes an invariant cannot be expressed as a C++ expression. An invariant can be that you have a unique access to some resource. You have acquired the resource and you own it for the duration of the lifetime of the object. This is also an invariant, but there is no expression that will work. And the other reason is when we want to provide the interpretation of the value that is unique to our use case. And there is also a third interesting case, like in function length, when it almost looks like we could express it, the precondition of this const star, but we actually cannot. It's obvious that we don't want this pointer to be null, but the other part of the precondition is that the array it points to has to end with 0. But there is no way to check it. The only way to check it would be to iterate over the array and see if there is 0 at some point. But if there is no 0, we'll never stop iterating and we'll have undefined behavior. And again, wrapping it in a class solves this problem. We have a class, it's just const star, and we have an invariant, even though we cannot express it. But if we speak in terms of this class, which is somewhat similar to string view, we can get everything safe until at some point we reach an API that actually needs to talk in terms of const star. So our class will have to have a constructor, maybe a converting constructor. In C++20, there is another way of saying that you want it to be a converting constructor, a more explicit way with this explicit false. And this constructor will have a precondition, which again, we cannot express in the language. But there is still a value in doing this. There is no way we can ever turn it into a runtime checks, obviously, but there is a possibility that we can engage a clever static analyzer to detect bugs for us. Now I'm selling you a fantasy because I don't know of any tool that actually does it, but it's conceivable that such tool would be created because there is nothing stopping us here. Imagine that there is this attribute that does not exist today, symbolic. And with this symbolic, we could define our function, probably inline, give it a good name like isNull terminated, and have it return true. And the meaning of this function is, if it is evaluated at runtime to check the precondition of a function, it returns true. So we don't want to return the false positives. It means that we couldn't determine that there is a bug. And it will not help any runtime checks. But if it is evaluated as part of static analysis, that does a symbolic evaluation of the program, we instruct the static analyzer to treat this function as a symbol. Don't look inside the implementation of the function because it's just mock. or treat it as a symbol for the purpose of comparing it against other symbols in the program. What we gain from it is, first, it is actually a function that you can call. It has a name, so you can call it, pass it arguments. So even if you cannot evaluate it in a meaningful way, you can express it, use it in an expression. And now if there is something like getName that returns an ordinary pointer, and our function length has this precondition with is null terminated, static analyzer will, let's go back, report that we have potentially, not necessarily, but potentially a contract violation. But if we manage to also get this function getName to have a postcondition, now we are talking about postcondition, so something that we guarantee of the return value. Return value doesn't have a name in a declaration, so we have to artificially introduce this name R, and then say something about this variable R. If the symbol here is the same, is null terminated, as in the precondition of the other function, the precondition of one function is matched again the symbols there, as the postcondition of the other function, and the static analyzer warning is silenced. And we introduced this way a notion of a postcondition. And the most useful thing you can do with the postcondition, as I see it, is to match it against the preconditions of other functions. Postcondition is not always bound to hold. It only holds when two conditions are met. First, when the function does not report a failure. Usually, we report failure by exceptions. So if our function throws an exception, it means it cannot satisfy the postcondition. So it's either every function either guarantees its postconditions or reports failure. And in fact, if we throw, there is no return value, so we would not even be able to inspect the return value to determine if it's fine. And another thing is postcondition only holds when you take care of the preconditions. You have to satisfy the preconditions, and only then can I satisfy my postcondition. You can easily imagine this with the function is better here. Whereas function is better that selects better of the two integers a and b, and we expect that all those a and b are non-negative. And it's obvious that if you pass me a negative number nonetheless, I will probably return it. And this is fine. I am within a contract. You are not. Okay. Now, what can we add to the language to enforce our contracts even further and to help avoid bugs? So far, I've been showing you comments. Comments are a very useful feature. They can express almost everything, but they are just for humans to read. Only humans can understand comments, and maybe you can teach a single individual tool to understand them also, but they are not understood by every tool there is in the world. So they are not universal. We've also seen assertions or macros in general put inside function bodies. They are very useful. They help prevent damage, as we've seen. They can help in testing, but they don't actually prevent bugs. The way they work is that you have to first plant a bug, and then maybe we will detect it. And it's even worse with the postconditions if we want to express them with macros, because if we return temporary values, if we build them on the fly, there is no place where we can actually put a postcondition declaration. Like here in this function, I just produce a temporary value. I cannot put my postcondition macro before this return statement because there is no return value yet. I cannot put it after because then it is too late. I have to change the implementation of my function so that there is this value R, which I can inspect. And now I have made the code longer, and I have probably compromised the return value optimization. And it's even worse when we have multiple return statements because we have to put the postcondition on every one of those, and we will likely get it wrong. So this is where contract annotations would help. This is what I would expect of the language to provide. An annotation that I can put on function declaration, which helps me to declare the preconditions and postconditions to the function. Of course, I can, like in case of pointers, I can only define a subset of the real precondition, but it's good enough. So I would be able to say this. This looks like an attribute, but it's not really an attribute because we have this column, and columns are not allowed in the attribute here. So it's only similar to attributes. I am allowed to put an expression here, and the compiler will check if this expression would compile. And because of that, the compiler has the liberty to inject this expression actually if it's instructed to at some point. What we gain from this is that we are able to communicate our contracts, the set of disallowed values, universally to every tool in the world. And with this, we enable the same bug detection experience that we get for language contracts, like null pointer to reference. Now, the examples I've shown you with static analyzer always involved making our function inline in order to expose the body of the function to the static analyzer. If we had those contract annotations, this is no longer needed because all the information required by the static analyzer is exposed in the declaration. And the definition can go separately. So there's less computations that a static analyzer would have to do. Also, you will be able, to put those in the places where you cannot put macros. Like in case of invariants, it would be a declaration inside a class definition. And here is one interesting use case that the IDE could make, which is not even related to static analysis. Like imagine that I am using this function isInRange that has a predicate, the contract annotation on it, expressing the precondition. I'm using this function. I think I'm using it correctly. I ask my colleagues to do the code review. The code review passes, everything is fine. But my IDE, which can read the declaration, gives me a hint that I am expected to satisfy this precondition. Upper is less than equal val. So it's not copy pasting the text because it's substituting the names of function arguments and remapping them onto the names I use in this scope. So they were called val, high, low, and here I'm using words lower, upper as in my scope. And you can immediately see that something is wrong with this precondition. The goal of calling this function is to check if the val where it is located. Bigger than upper, lower than lower. And the precondition tells me that the val already has to be greater or equal than upper. So something is wrong here. The IDE will also show me the declaration here. And because they are all put together, this is what IDE can do. It can bring different parts of code together. I can immediately see that upper got mapped onto low, val got mapped onto high. I confuse the order of arguments. I know I don't even have to compile this program. The IDE has found the bug before I even planted it. Similarly, or maybe not similarly, not static analyzer, the UB sanitizer could read all those preconditions and inject runtime checks based on my preconditions. Again, this is upper greater than val. So it looks strange, but this is because I confused the order of arguments in this function. So it can inject runtime check and call abort. So maybe it would no longer be called UB sanitizer, but a contract violation sanitizer. And we could get this automatically only because we can officially declare our function contracts to everyone. But there are also costs to this feature. Like we already have multiple ways of obfuscating our function declarations by saying it's const, per, override, virtual, no accept, no discard, no return. You can put all this stuff here. And now if we add to this set the ability to add preconditions and postconditions, if we add to this that precondition can have arbitrary expression, if we add to this that lambda can turn any expression into arbitrary sequence of statements, we can get a real mess. Like, can you see how many members are declared in this class and what their names are? Good luck with this. I'm not going to help you. Now it looks like we have a couple of minutes, so let me show you the difference between fixing bugs and concealing the symptoms of bugs. This is a piece of code that first gets two aircrafts with this function getAircraft, and then checks which one is lighter. And this function getAircraft has a postcondition that it will never return a null pointer. So what it means in practice is that it will probably throw an exception if it didn't find aircraft by name, because the contract is usually I either throw exception or satisfy the postcondition. So because it can potentially throw an exception, someone has typed try catch 3 dots / to do handle it later. I've seen it a lot in the code. And now, because there is the possibility that this happened, we may end up with a null pointer. So we have to check at least one of them. And only then, if one is null, we just skip the code, parts of the code, and otherwise we call function is lighter on X and Y. And obviously it has a precondition that those pointers cannot be null. If we run it through a clever future static analyzer that actually can understand the preconditions and postconditions, it will tell us that there is a control path in this program that leads to this function isLighter being called with Y being a null pointer. The static analyzer doesn't know where the bug is here. It doesn't understand our intentions. It only knows that it couldn't have been our intention to call a function out of contract. This is all it knows. The rest is on you. You have to fit. So it discovered a symptom. But what the bug is, it is a quest for you to find. And this quest can take 10 minutes, half an hour, 2 days. But the programmer has to do it. So what an inexperienced programmer will sometimes do is to type this. Okay, if this is a problem that Y is passed with a null pointer, just check if Y is null, and if it is, just skip this code. But this actually doesn't solve the problem. No bug is solved by skipping random parts of code, because this code is there for a purpose. So this doesn't fix the bug, but it makes the situation worse, because the bug is still there, but now the static analyzer cannot see it. If our goal is not to see static analyzer warnings, there is a simpler way to do it. Just disable the static analyzer. It's fewer resources, more time gains. It's much simpler. Static analyzer only gives us an indication that there is bug somewhere, and we have to inspect the entire neighborhood here. And the real problem is in this premature try-catch statement. Like, if function getAircraft produces values, and then this isLighter function consumes the values, they cannot be separated by a try-catch statement. They have to be put together. So the real corrective action is to put this isLighter inside the try-catch block. And now we don't have to do any if statement here, because the logic of stack unwinding does it automatically. This is the whole point of doing stack unwinding, to skip the operations that depend on the previous operations. So we get that for free. And now we can see that, of course, the problem still remains that we catch an exception and we don't know what to do with it. Because again, this is the point when you try and catch exceptions at random places, you don't know what to do with them. The only thing you can do with them is to throw them up. But if you catch the exception only to rethrow it, you might as well not catch it in the first place. So we can drop this. And if we drop this, the only purpose that we separated the declaration of X from the value assignment was because of this interleaving try-catch statement. Now that we don't have it, we can merge the declaration with the value assignment, and we arrive at this code. Now we can say it is fixed. It's not only more correct, but it's also cleaner. This is how you fix bugs. So a warning is just a start of a quest, which is time-consuming. Therefore, the static analyzer try hard not to give false positives, because if they did, no one would look at them. And that's it, what I had for today. I finished earlier than I thought I would. So just to summarize what we discussed here, it's all about function contracts. We can do a lot of things with them, provided that we actually define and communicate our function contracts. This is the most important part. And an important characteristic of them is that they are not expressible. Function contract only belongs to human communication. And we can only try to express parts of them as language features, like better classes with constraints and those contract annotations. And those contract annotations, which is something new apparently, and we try to standardize them, are not primarily about runtime checks. The runtime checks is the first thing that comes to mind, but they can offer far more. First, they provide the same bug detecting experience as you get for language contracts. Every tool can understand them and make some use of them, like static analysis, better IDEs. And they also help human communication, because we pay more attention to declarations in code than to comments or HTML documentation. So this is it. I think I'm done. I think there is a couple of minutes to start a discussion, because I don't expect everyone to agree with what I said here. So if you feel you disagree or you want to ask questions, the floor is yours. Okay, so there is a comment in the chat. In safe numerics, there is a safe range int min max, which is not mutable. The min and max are part of the type, so there is no runtime cost, yet still enforcement of the invariant without depending on analyzers. Let me think about it for a second. And there's Arthur's comment about, there is a great argument for avoiding mutating functions for purposes like this. Example doesn't mutate. So I'm not entirely getting this, but I can switch you I can offer you a voice over the microphone to ask this. I can see a question here. Are the contract annotations shown in this presentation the same thing that was proposed for C++20, but did not make it? Similar, a bit simpler, because I didn't talk about the levels or of the sort, but yes, the syntax is very similar, except that I I also showed you how you could make invariants with it, and invariants were not proposed for C++20. But otherwise, yes, I reuse the syntax. There is also a possibility in this online conference to answer the questions over the mic. So if you want, just raise your hand and I will give you the voice. Can I understand from your talk that to produce an abort is better than hide an error? Yes, this is what I tried to communicate. By default, unless you have some other reason to believe otherwise, but in the generic sense, I find this to be a better default to abort than to produce random results. You mentioned you are participating in the contract study group, right? Yes. Is your symbolic idea basically the same thing that contract spell per axiom? Last time I looked. Yes, they are similar, except that in the previous attempt, C++20, the axiom was part of a precondition declaration. And what I'm showing you here is that the axiom or this symbolic goes on the function, on the predicate, rather than on the function. So our function length does not know that is null terminated is actually inexpressible. It thinks it is calling a normal function. This is the difference. So I annotate is null terminated with this rather than length. In C++20 axioms, I would have annotated the length that it has predicate with axiom level. Is the contracts proposal still alive and being worked on for C++23? Yes, we are still working on to add contracts to the language. It will be a smaller subset than what we seen for C++20. But the goal is to get them. Not sure if for 23, but for 26. You never know how it is with timing. We still have a couple of minutes for questions, but if this is a long question or if you're not comfortable asking it here, I think when this talk finishes, I will go in this gather tool to the room called the Boost Library, and we'll wait them there for half an hour. If you have any other questions later, we can chat there. Also, this is a contact where you can reach me either over email or through my blog. What is being removed from the concepts? I understand it's contracts proposal. This for C++20. We don't want, in the first iteration, we don't want to add those levels like audit or axiom. They may be added later, but for now we want something simpler. Simpler that you only express the precondition, you don't say what level it is. Other thing was with the continuation mode. We do not want this. And the big controversy was about undefined behavior introduced by contract predicates that were not checked. So if you disable checking, the previous specification said it would be undefined behavior if the contract was violated and people didn't like it. Because the primary, at least this is my opinion, the primary gain that you have from contracts, the minimum that they can give you, is for you to be able to write your preconditions down. Not necessarily that they are evaluated at runtime, but that you can express them. And you already unblock many tools, many static analyzers, IDEs, only because you can communicate what you consider to be wrong input to your function. Oh, and also the previous contracts said a lot about the violation handler and how you would install a new one, what signature it would have. I think that for the C++23 contracts, we would skip this. Again, this is to be first to be able to even express the contracts. And then in later incarnations, we can add features on top of this. Oh, there is a hand. I think you can already speak, Robert.
Yeah, I think I can. Can you hear me?
Yep, pretty good.
Okay, the point I was trying to make in this chat is I think your talk is a good explanation of one of the concerns that I've had for a long time, and my approach to it is quite different, but it has some similarities. And I just and in the chat I posted a little bit of what those differences are. And if you'd like, I can expound on them through the microphone, but it's up to, or you can just not start up another back and forth if you like.
Sure, we have 3 spare minutes.
Okay, so I'll give this a shot here. I get what we're looking at. We got a type which contains a value, and we want that type constrained between a minimum and a maximum, or a low and a high. And we want to be able to count on that invariant wherever we use that type, so that we won't be introducing any bugs because the low the low and the high are interchanged, or the value is outside of the low or high, or etc. So I'm pretty sure that that's the idea that we're communicating here, making a truly safe type that can only hold about a valid value, and thereby eliminating a source of bugs and providing something that we can count on to be true at any point. Have I captured that correctly?
Okay, will I be able to handle it in 2 minutes?
Well, okay. Let me just cut to the chase here. In the safe numerics library, which you're pretty intimately familiar, I have an object or a class called safe range, in which you specify the minimum and maximum value, and those minimum and maximum are encoded with the type, so that they're available at compile time, and they're available whenever a value is assigned to that range. And so a lot of the range, the checking on the ranges, et cetera, is already built into the type system, doesn't require dependence on static analyzer or anything of that nature. So that's, that's encoding the limitations in the type. For your example here, I think works better, or at least when I thought about it, I came to a different conclusion. And I'm curious if you had any comment on that.
Okay, so I think I get it. I was always a bit uncomfortable how the safe numerics works, because the way I understand it is okay to pass too big integer to this constraint int. It will just throw an exception if I do. And it looks like everything is okay. I passed a bad number, you threw an error, and we're happy. And I'm not happy with this, because my goal is, for me, never to pass bad integer values from the outset. It's like I have to produce a bug, and you will be able to respond to it.
No, well, the thing is, the type, an instance can only be, the only possible instance that can be created has to be a valid one. That it's impossible to create an instance of a type of safe range which has a current value which is outside the range which has been defined at compile time. So the whole idea of the only time you might get a bug or a exception or whatever is in the constructor when you try and create a value with a value which is outside of the predetermined range.
Yeah, and this is this constructor that bothers me, because otherwise, if we are past this, yeah, then we are fine. You don't actually have to check anything anymore, right? Because
Voila.
you will not produce bad values once they have passed the test in the constructor.
Correct.
So it's only this constructor that is an issue and is the core, I would say, to
well, even the constructor, if you pass a value which is outside the range, which has been encoded in the type, it will give you an exception right there. You don't have to write any extra code. It will not permit you to construct a value that has a value which is outside the predetermined range.
Yeah, so this way you guarantee that your class always maintains an invariant.
Correct.
Which I think is fine.
Okay, well, as I say, I think that's quite different than what you've expounded upon here, because you don't actually have to create any other code, and you know at 100% that the instance that you created is created correctly and is always correct.
I mean, in the example with range that I show, I trust you. It's just, I trust you. I don't check it in the constructor.
Yeah.
I just hope I assume that there are no bugs in the program.
Yeah,
I could do a check there, but what would that mean? It means that I allow you to plant the bugs, and then I will respond with an exception. I don't like it because it's still a bug. I don't consider throwing an exceptions as a tool for communicating bugs. Bugs should be removed from the code, not signaled by exceptions.
Okay, well, all right. I've failed to be convincing, but you know, I'm still got a lot of years left, so we're not done yet.
I think we need a longer discussion here.
Yeah, of course we do.
Okay, now we are past the time, so I think I have to stop it. So thanks again for participating.